So good morning, everyone. And it was a very interesting conversation as we just started. Okay, so this talk is the title sort of says it all, basically about information, physics, and machine learning. And probably it will contain a bit too much. And I will use math, and maybe more than usual, but the math will just be to explain things. I will not actually go through the real calculations. It's just to give you flavor. I will just explain the final results. So don't worry about if you're not following any equations. There will not be too many of them, but just in case. Okay, so the first question, of course, we want to answer, and the main question we want to ask really is, what is information? And of course, we all know what information is, but still we don't really know what it is. So here's an example of information. It's a newspaper article from 3 years ago, almost 3 years ago by now, in which you can hopefully make out some of the words. So I randomly remove some letters, vis-a-vis asterisks. And as you go down this article, you can, in the beginning, the first line, you probably guess quite well what the asterisks stand for. There's only one possibility that makes any sense. But as you go down in the next line, and the next line, and in the fourth line, it becomes more challenging. So the point that this trivial example wants to make is that you can compress information. You can remove some letters and you still know what's going on, but you cannot remove too many letters, obviously. If you remove the whole story, there's nothing left. So the question really is, how much can you compress information? If I give you some newspaper article, anything that you want to look at, by how much you can compress it. And that relates deeply to entropy as it appears in computer science, in bioinformatics, and quantum information, and many, many other fields. Okay, so here is the actual article. If you couldn't, and I'm certain most of you, if not all of you, including myself, when I first saw this, when I first made this example, couldn't make the whole article out. But here's the actual article. So there's some paper, the Eiffel Tower, and he was doing some crazy stuff. But the point is not necessarily the article itself. The point is that you can actually make sense of the article, even if some letters are missing. And this compression of information, as I mentioned a few seconds ago, also appears in other fields, like, for instance, bioinformatics. So here's a DNA molecule. Of course, as most of you know, is comprised of these base pairs. It's double helix. And these base pairs, A, C, T, G, and always come in pairs, they are formed from alphabet, if you want, and there are 4 letters of this alphabet. And you can ask, how much can I compress? How much information is stored in the DNA? Of course, a lot of information is stored in the DNA. Of course, it makes us all. Much of that information from the DNA that makes us all is actually just junk. It's from old viruses and so on. But much of it, of course, but still, it's very, very crucial for us. If you take it out, you all die. So certainly, we can compress information. The question is by how much. So that question was actually the one that Claude Shannon was thinking about over basically almost 35 years ago by now. And so he was thinking about communications channels, and he was a mathematician and engineer. He was really an all-round person. He really had many hobbies and contributed deeply to many fields. But most importantly, in my opinion, to information theory. So this is sort of a key idea. You see that you have original data in the top line, okay? And then you can ask, can I compress it with no errors whatsoever? Of course, there might always be some errors, but we wanted the errors to be so insignificant that we can really not worry about them at all. So can you compress information with errors that basically don't exist by somehow? And by how much can you compress it? And of course, it's used all the time when we do recordings of videos and so on, satellites, you name it. It's all around us without even realizing it's all around us. So here's some pictures of Claude Shannon. So he was a genius. He did many things. He invented, for instance, a maze back then, over 70 years ago, in which there was a mouse that was actually solving the maze. He was going around solving the maze. He made one of the first, if not the first, chess computer. And he was a part of that chess computer that he designed. Okay, so here's the actual question we want to ask ourselves. Let's start off with the simplest possible thing. Okay, suppose that you actually have, can you all see the full screen? Okay, just to make certain. Suppose that you have a coin which is not fair. That is to say, it always lands the way that you want it to land, or somebody else wants it to land. clearly, if it falls, if let's say it's supposed, quote unquote, to land on heads. So clearly, if somebody tosses a coin and it lands on heads, there's no information there because you already knew it always lands on heads. There's absolutely no information. So the information content of that, the so-called channel entropy that you have associated with that particular event, for one event, well, there's actually a difference between information content and channel entropy. We'll discuss that momentarily. But for one single coin toss, the information content that you actually have, if it's completely unfair, it's zero. You know exactly what's going to happen. So the probability that it lands on heads is 1, or probability that it lands on heads is 0. In either case, you know exactly what's going to happen. On the other hand, if you don't know what's going to happen, there's a 50-50 chance it might be on heads, it might be on tails. Clearly, the outcome conveys some information, and it conveys 1 bit of information. You can actually write down a 1 if you have the heads, you can write a 0 if you have the tails, and there's no a priori bias to either having a 1 or a 0. Of course, some events, there's been some challenge whether the actual coin toss was fair or unfair, as you might know in some sports games and so on and elsewhere. But for a fair coin toss, this is, of course, what we want to have. Okay. So the information content is defined by Shannon is this equation you see in front of you. Basically, it says that if you have a coin whose probability to land on heads or tails is the same, that means a half, then the coin toss gives you 1 bit information, either a 0 or a 1 with equal probabilities. So 1 over probability, 1 over a half gives you 2, and the 2 is to the power of 1, hence you just need 1 digit, 1 bit in binary format to convey that information. Clearly, as the event becomes more and more rare, suppose that you have 2 teams, and one team always wins in this match. But for whatever reason, the underdog actually won. So if there's a newspaper article the next day that the underdog actually won, that conveys important information. On the other hand, if a team that always wins won again, who cares? I mean, people care, of course, but it doesn't convey that much information. So the more rare the event is, the lower the probability is, the higher information content. And that's exactly what this equation conveys. Okay. So here's an example that you probably all played around with as kids, or maybe play around with your own kids or grandkids. So you think if you're in the car as a kid and you're asking your siblings and so on, think about some number, the number between say 0 and 63 or whatever, 1 and 100. Don't tell me the number, I'll guess the number. Is it larger than this? Is it smaller than that? You know, you keep asking questions, and you typically what you want to do is to divide the region that you ask the number about into halves. You start from say 100, divide into 50. Is it larger than a 50? No. Okay, I'm going to go from up to 50. I'm going to ask again up to 25, and so and vice versa. Okay. So overall, suppose you have a number of 51, and you keep asking these binary questions. Is it larger than that? Smaller than that? Essentially, what you end up in the end is this binary number. And the binary number, the number of questions required is, of course, is equal to the logarithm based on, say, the power of 2 that will give you this number, this range that you actually, of numbers that you ask to find the number in. Okay. So this is sort of the case. And of course, if you divide by 2 sequentially and you look at the remainders and so on, you can write down, and we'll start the remainder, you can write down the binary format is automatically. But the point is that the number of bits required for that is equal to the power of 2 that's equal, or greater than equal to, if it's not exactly equal to that, the range of numbers that you have. So the point is the following. If I have lots and lots of numbers, I have lots and lots of possibilities, as you've seen this cartoon in front of you, the nice pictures of 3 blue, 1 brown always has. So suppose that you have all of these possibilities, as you see on the left-hand side here, and you want to find a number, the possibility that you thought about or actually occurred and so on. If for more possibilities that can occur, like say all the numbers can be equally probable, then clearly you have to work harder to find what the number is. You have to ask more questions. The number that you actually are looking at is more rare. The more possibilities that you have, the more rare the actual number that somebody chose or you chose there. So you have to have more and more steps to actually find a number. And again, so if you have a power of a half, because you want to divide your region into half and never half and never half, as we just discussed. List of numbers will be given by the logarithm base 2 of this probability, of one of this probability. So that the more unlikely the probability is, the more rare it is, the larger the content. Is this clear to everybody? Okay, I hope this is clear. This is a really important bit, literally and figuratively, no pun intended. Okay, so now let's go back to this text message I showed you earlier. This is the article. And we want to ask, so clearly as you look at this article, as I just mentioned earlier, and as you all hopefully figured out some of the missing characters there and so on. Some of them not necessary. So pretty clear. The officer is the first word that has an asterisk. It's the only thing that actually makes any sense in the current sort of context is having that thing being an R and so on. So you can compress information, and some letters, some are more likely than others, and then of course you can look at the actual context that you actually have. What does it make? It's like a puzzle that you have to solve. Okay, but not all letters, of course, are equally probable. Not all words are equally probable. So, for instance, you might know. I'm not sure I cannot move down. Okay, so you might know, for instance, that there are these rules about how probable or improbable things are. For instance, if you look at the English words in English language, or any language for that matter, and you rank order them, you say the most common word I find in all texts is the. The next one is of, and then that, and so on and so on and so on. And then we have a rank. Number one is the, then I have off, and so on. And I look at the probability, that the frequency that they occur at, okay? And I look and I find out that it basically behaves as one of the rank. And this is universal. This was discovered long ago by Ziff. There are some models that explain it, but empirically, this is exactly what happens across the board. Even if you look at the smaller text, like Romeo and Juliet, and you try to look at what happens there, again, you will find out that you have this nice law for the probability of different words. The same thing appears when you look at people write checks and so on, or anything that you have. What's the probability that the first digit that you actually have in the check is equal to 1? What's the probability it's a 2? What's the probability it's a 3? It turns out that if you have some number, you look at numbers of a very, very broad scale. It's not like looking from 1 to 10 or something. It's a very, very broad scale, and all scales can exist with equal probability. And the probability of the first digit actually has a particular value follows this nice rule. So if you're looking at base 10, from 1 up to 0, up to 9, you're looking at probabilities that you actually have everything first digits. We're given by this. D here is the first digit. So people can ask, are elections fair or unfair and so on? I'm not going to get into politics, of course. But people sometimes do tests to see how likely is the outcome of an election. Does it make sense in terms of probabilities? Does it satisfy it or not? And so on. And there's lot of literature about that. But the point is that there are rules that we have about what makes sense in current context, like these articles. And more broadly, there are probability distributions that we have even just overall. If I just choose a random word out of the hat, what's the probability that it's of? Will be 3.5%. Okay, so hopefully I got you got the message, the information that we can compress information and up to a point, and there's context that there's of course implicit always there, which we can use to our advantage. And the question is, if I give you now, and this is the question that was posed by Shannon, Clark Shannon, in 1948, to solve this problem. If I have now a stream of data, someone's communicating for you and so on, and he or she sends you data. And let's imagine they send you one letter per one character per second or per microsecond or whatever it happens to be, millisecond, whatever it happens to be, that how fast they actually can text you and so on. Of course, some can do it milliseconds, but can be pretty fast. So how fast? So what's the probability that you have per character, per event? So the information content itself, as I just explained to you, I'm motivated for you, is the logarithm of one of the probability. The more rare it is, the more information it has, the more likely it is, less information it has. If I now look at the average value of that information, that's nothing else than the entropy, the Shannon entropy. That's it. Okay. And if I use this particular simple equation, again, if you don't like equation, don't worry about it so much. But the point is, if I just use the average value of the which content that I have per character, that tells me exactly how much data I have to save to communicate something with a negligible error. Okay. So one guiding principle across diverse fields is that of maximizing the entropy. Okay, so if you have high entropy, that means that the thing that you're looking at is on average quite unlikely. Okay, it means that you need more possibilities that can actually occur. You don't know which one of the possibilities actually is going to occur, so you have to work harder to find out what it actually you have. So if you want to look at something which is the most random, that you need more and more information to actually find exactly what it was, that will have high entropy. And if you want to look at some event and so on, and or what is likely to occur, typically what you want to do, as a rule of thumb, is you want to maximize the entropy. And typically you might have constraints, like you have to have something else being satisfied, another being satisfied, and so on. But typically what we quite often do, knowingly or unknowingly, is we maximize the entropy given some constraint. Suppose we hear some word, we don't exactly know what that word, it sounded, somebody far, far away talked and said something, we couldn't hear it so clearly, but let's say, what it could possibly be that it would fit in the largest number of contexts that it actually could be in, that for which we would have some information, that would correspond to exactly making out what that, figuring out or guessing what that might be. Here's an example. I'm not going to take you through all the steps of this example, but some of you might know this example, some of you probably might not. It's a classical problem that's been around for decades. Suppose you have a pan balance, like these old-fashioned pan balances people used to have in markets and so on. Or sometimes you find courthouses, they have to weigh, literally, they have to weigh the judgments that can be coming before them and so on. So you have a pan balance. Pan balance can either be right, can be left, or it can be balanced. Okay. Suppose that you have 12 coins. You have these 12 coins. And one of these coins is actually fake, by which we mean that the coin is either heavier or lighter. We don't know if it's heavier or lighter. It's just not the same as the others. And your task is to figure out which coin is a fake one using your old-fashioned pan balance. And you might ask, how do I do that? What measurements do I have to perform to zero in on that coin, a fake coin? Okay, so one of the ways, so you can of course, think about it. Okay, do I do this? Do I do that? Maybe if I do this, I'll get that, and I do this, and okay, look at all possibilities and so on. It might take some time to do that. Of course, you might be very, very smart or very, very lucky or both. But if you just want to do it in sort of just without thinking, just figuring out what should you actually do, you basically can maximize the entropy. You can say, what are the possibilities here? How much ways do I need to do? Okay, so I can ask you what is in my classroom, but if it was in the classroom in person, I would ask you, do you think you need 13 ways to actually find a missing coin out of the 12? 2 of them, 3 of them, 4 of them. We will take a vote and we will see who wins the vote and so on. We can't do that, and so readily here. But what we can do is we can basically calculate directly the entropy. And suppose, for instance, that I have 12 coins, I just showed you earlier, so now I might have 10 fingers, but I have 12 coins. And I put 6 of them on one side, 6 on the other side. And of course, because one of the sides will contain a fake coin, it will tilt either left or right, okay, clearly. There are 2 possibilities. And if I calculate the entropy, I have a probability that half it goes to the right, and probability that half it goes to the left. So I just plug into the equation and get 1 bit. Not surprisingly, because I have 2 possibilities. It can be left or right. So, there's only 1 bit, okay? What about if I put 5 coins on each side of the pan balance? I put 2 on the table, and I calculate the probability that it's on this side here, one of these 5 is a fake coin. I have 12 of them, so it's 5 over 12. Probability that the fake coin is here, that it's going to tilt this way and so on. Is again, 5 over 12. Probability that's equally balanced, meaning that the 2 coins that I have on the table, one of them is a fraud coin, the fake coin, it's 1/6, it's 12 and 12. So I can keep going and going and going. I'm not going to take you through that. But the point is I can calculate all possibilities, and I can figure out that the probability that the one that has the highest entropy is putting 4 on one side, 4 coins on the other side, and having 4 coins on the table. That's the most likely, that's the event having the highest entropy. And so if I want to maximize entropy, I should do that. And I'll do that. Okay, and it's not terribly surprising as you can read here. The point I want to make is that, it's, if you have things being equally likely, then it has the highest entropy. It's most random. So if I have 4 here, 4 there, 4 there, it's most likely that any one of these possibilities of either tilts to the left, to the right, or doesn't tilt at all, it's bounced because the one on the side is the right one, what contains a fake coin. It's all equally likely. So that has the highest entropy. Okay. But the point is that you can keep going and going and going and have put full algorithm doing that without even thinking of what's going on, just by calculating the entropy. The same thing you can actually do with this game that some of you might know called Wordle. And again, this is a nice video by 3 Blue 1 Brown, and he was using this to illustrate the concept of entropy. So the game, in case you don't know, is that you have to guess a word, hence the name Wordle. It has 5 letters. Okay, there's a list of words that I think it can actually be. You can actually go and see the possible list of words. And what you do, you guess a particular word, and it tells you some of the letters that you guessed are actually right. You say the green things that you see here, the W and the A at the bottom panel, the W and the A are in the word at exactly the right position. So the first letter is a W, the third letter is an A. Okay. And if I ask about the R is there, but it's not exactly the 4th position, it's somewhere in this word, but not at the 4th position. So looking at that, you sort of see, well, I have to find a word that satisfies these constraints. It has a W in the first letter, an A is the 3rd letter, and R is somewhere else, not the 4th, not the 3rd or the 1st. So clearly either the 2nd or the 5th, and what can it possibly be, and so on. So I just keep guessing, and I have 2 letters which are not right, the E and the Y are not there. So I guess possible combinations, and for each possible thing that I guess, I can assign a probability. I can have a probability. You can calculate the entropy, okay? And you can find out what word is the best one to start off with, which one has the highest entropy. I can do it just on the first word as overall. I can do it marching into the second word or marching into the third word and so on. And it turns out if you do this all the way through, the best word to start off with is a salé, which is basically, it's the word that you know about, but basically, again, this is your 3 Blue 1 Brown, but basically it corresponds to a helmet that has a protection that you have at the back of the neck. Okay. But in terms of probabilities and so on, this is the highest thing that you can actually come up with. Okay. So you sort of see that in general, in many cases, in this simple examples of word games and coin games and other situations, much more practical situations, we want to maximize entropy. Okay. And if you start just at the first position, you might be lucky, as we were earlier in the case of hand balance, just moving one move through gives you the right answer. You can actually have to work a bit harder, have 2 moves through, 3 moves through. But the point is that you actually get a good deal of intuition and in some cases also the right answer to find out how to solve the problem. So one of the pioneers of information theory, in particular maximum entropy, actually was here. Some of you might have known him. I did not know him. I came to this department after he left. His name was Edward James, and he wrote pioneering papers on books about this topic. Okay, so here's an example. Again, I'm not going to go through the math. I'm just going to flash it for you of why we can compress information. So I have a big disk containing lots of information. I want to compress it to something much, much smaller file. How much smaller can it possibly be? Or as an example, again, this example is just a variant of an example that David McKay wrote a fantastic book about this. But there are many possible minor variations of the same basic idea that people had for some amount of time. So basically, the point is to find, suppose that you have a lottery or you have to find some material or whatever the case might be. And there are lots of possibilities. Suppose that you have a lottery in which you have 1,024 lottery tickets. So you have, let's say, you can write them in binary form, and the first digit can be 0, 1, it can be 0 and 1, all the way up to the last one. To the power of 10 is 1,024. Okay, so now you just, and you want to find out, so suppose that you want to buy lottery tickets and you want to win. Okay, of course, the probability of winning in the lottery is not terribly high, it's not advised at all, of course. But suppose that somebody has a gun to your head and tells you, I want you to win this lottery. I'm going to give you money, but don't waste my money. I want you to win this lottery. Okay. Well, you might say this is an impossible task. I'm certainly going to fail. I'm going to die. But with this this awful person is going to shoot me and so on. But suppose that the lottery is not completely unbiased. Suppose that the probability of the 1 and the 0 is not the same. Okay, so the probability of the 0 is 90%, the probability of the 1 is 10%. Okay, otherwise, of course, all numbers are equally likely, and clearly you would need 10 bits of information to find out what is the right number. Okay, so now you ask, okay, let me buy my first ticket. What should I buy? Should I buy all zeros? Remember, the probability of a 0 is 90%, probability of a 1 is 10%. Again, if it was in the classroom or lecture hall, I would ask you to raise hands and so on to see what you're thinking about. We don't have that luxury of doing it. But imagine if you just ask, okay, this person's going to really just offer thing to me. I do have to do something. What should I do? Should I buy a ticket of all zeros? Should I buy a ticket with 1, 1? Does it matter where the 1 is? Should I buy tickets of 2 1s? So most people actually think that initially you have to buy a ticket with 1, 1 because the average value, the 10% of probability of having 1 is if you have 10 digits, you have to have, you're most likely having 1 somewhere along this line of 10 digits. But it turns out actually that the highest probability, and again, it's not really surprising, but you have to think a little bit more. The highest probability is that of having all zeros because it just, any given position that you have, the first, second, the third, whatever it is in the string of digits, you're always most likely to have a 0 vis-a-vis 1. It's true that on average of all possibilities, you're most likely to have 1, 1 somewhere along the line. But that's somewhere along the line, not I think you have a particular location. So the most likely ticket that you actually should buy is one of all zeros. And that's not terribly bad. In fact, if you buy all zeros, the probability of winning is not 1, obviously, but it's 0.9 to the power of 10, which is pretty good. It's a bit more than 1/3. Okay. Now, if you can buy a ticket of all zeros and 1, 1 somewhere along this line, and that's of course a bit lower, you can buy these 10 possibilities that the 1 is anywhere along this line. First one, second one, third one, all game march all the way through. So you buy 11 lottery tickets, and you can buy more lottery tickets and more lottery tickets. And you want to do this, you want to buy these lottery tickets such that at the very, very end, the probability that you're not successful essentially is minuscule. Or if you're some number of standard deviations away from the most likely outcome. Okay, so you can do the math, and I'm going to do it for you. But the point is, you can ask, how many tickets do I need? So I have N, this capital N at the very, very bottom of your screen, for generality, corresponds to the number of the digits that I have. So I have 1 ticket of all zeros. That's the first one that you see in the bottom equation there. You have 10 numbers of 1 in the first location, or second location, or third location, and so on. So you have 10 of those. That's the N that adds to the 1. Then you have 2 1s that appear anywhere in the string, and there are 45 of them. Okay. Then you have 3 1s, and so on. And you have all these binary combinations, these lottery tickets. And you want to sum them up, or number up, such that the probability of losing is essentially 0. And you can do that. You can just sum this sequence that you have on top, make sure it's essentially 0 by making sure that some number of standard deviations away from the average value. And then sum the bottom. When you sum the bottom, you find out that it's basically equal to 2 times the entropy that you, 2 to the power of the entropy that you actually have for the string. So per coin toss, the coin is unfair, but it has a probability of 10% for being 1 and 90% for being 0. Per coin toss, you have some probability. So some channel entropy, this is this H that appears in the bottom equation. Okay, but don't worry about it. Per coin toss, you have some number of bits. And I have N of these. Now I have 10 of these guys. I multiply 10 times this average entropy that I have, this entropy that I have per character. And that's it. That's that's the number of tickets I have to buy, 2 to the power of that. And it's much more smaller than I need to buy. I don't need to buy 1024. I can buy a much more smaller number. I can buy a number which is smaller, more than 5 to the 100 from that. Okay, so I can save this guy that's pointing a gun to my head a lot of money, and I can win the lottery ticket for him. Of course, not guaranteed. There's always a probability that it's in those very rare events that I didn't buy. But most likely, with very, very high confidence, I actually bought a winning ticket, and he could be happy. Hopefully, he or she can be happy. They won't kill me, and so on. Okay, so the point is not this example. The point is that you can always compress information in this way. And the example you might say is artificial, is some lottery ticket of some probability. But it turns out that many distributions, if you look at, regardless of what they really are in the beginning, if you look what you actually have at the very, very end by the so-called touch limit theorem, they always approach the Gaussian distribution. And the sum that I flashed before you is exactly what you would have universally. Okay. Now, this concept of entropy is also, of course, very, very important in physics. It's actually started in physics, of course. And it's, of course, more fashionable to talk about it in black holes and information and so on, which we're doing right now. But I actually started off by thinking about engines and heat engines and so on. But let me tell you a bit about black hole entropy. This is not my subject, okay, but I'll just tell you a bit about it. So this is a black hole that we've seen. So you can sort of see image, so you can image what actually falls into a black hole over time, and sort of see that you actually have a black hole there and so on. This is an M87, it's a galaxy. And so you can really see it. It's, of course, this has been seen for some time. And we can see it in better and better with time, but we know that black holes exist for quite some time. Okay, and we also saw gravitational waves. And then, okay, so let's imagine that we want to think about the entropy of a black hole. And we want to do it in a sense of thinking about information. Okay, suppose that you're this person or somebody else is this person, and this person is falling into this black hole. Of course, this is not recommended. If you fall into a black hole, you basically die, especially a black hole, which is like a smaller black hole, because you have a huge variation in the gravitational field as you approach it, and your legs will be stretched much more than the head and so on. So you'll be basically shredded to pieces as you approach it. By the way, as you approach a black hole, the so-called cross its event horizon, that this is the point of no return, so to speak. So you need something sort of the speed of light to actually make it out. You actually don't notice anything. I mean, if you're not shredded to pieces, of course, you wouldn't notice anything in particular. You would just go through it. So matter just goes through it. On the other hand, somebody observing you would never see you actually falling in. Okay, in very reference frame, your heartbeat would slow down, and the clocks in your spaceship would slow down, and so on. It would seem like it takes an amount of time for you to actually fall into the black hole. But the point is not so much, that. The point is actually information. We want to think about information that the black hole has. And to that end, I'm going to again flash equations for you. Okay, I'm not going to go through the map. I just want to convey the ideas. We can write down the equation for the so-called event horizon. Okay, this is this radius of a black hole, beyond which we cannot skip. Okay, so if you have a black hole of mass m, then its event horizon is given by this equation. So Schwarzschild equation. Okay, this is G using constants of gravity, C is the light in vacuum. This is what it is. You notice, by the way, this is very, very important, that the mass of a black hole is proportional to its radius. Typically, if you think about a balloon or a sphere or something, or this object I have here, typically a crystal or something, the larger the crystal, the larger the balloon, the larger the balloon maybe by example, the larger the sphere, the solid sphere, the larger the mass is, but it goes as a volume. Here, actually, the mass goes as a radius. So the mass goes literally in the size that you have, not in the volume. This is very, very important. So now you can use the following, apart from the math, which is trivial, if you do it a lot, it's trivial. The important physics is the following. Suppose I want to find out if I have a black hole there or not. So what do? I send in a photon that has a huge, huge wavelength. It just tells me, do I have a black hole here or not? So I send in one photon whose wavelength is equal to the size of the order of magnitude of the size of a black hole. So the wavelength of this photon, this particle of light, is the size of this light, basically, this photon is the size that I have of a black hole. Okay, so it has a huge, huge wavelength. Okay, and if I have a photon and I have a wave, and I can calculate its energy. Its energy is in my nose, Planck's constant times the frequency, and the frequency is set by the wavelength and so on. So I'm not going to go through the math. So that's the second equation that you see in front of you. This delta E is basically, if I send in one photon in, I'm sending in an energy which is equal to the energy of a photon, and I know what that is. It's basically Planck's constant, speed of light, divided by the wavelength of this photon. But as it falls down into the black hole now has more energy because it swallows this photon, and we all know E is equal to mc squared. So energy of a black hole increased, so the mass increased by what Einstein told us. And now if I combine everything together and use the Schwarzschild radius, we find to our delight or surprise that actually this equation in the box holds, namely, this is a black hole increased by amount delta R, and this delta R is by how much it changed because of the incoming photon. This combination is equal to something really universal. It has no depends on anything apart from universal constants, like Newton's constant, Planck's constant, h, and speed of light and vacuum. So those of you that know calculus will recognize that this equation in the box up to trivial prefactors, is nothing but the change of area. So as a photon comes in, the area of the black hole increases by universal amount. It doesn't matter, how large a black hole was. If it was small or large, it was one we have in the center of the galaxy, or it was a much smaller one that we have, which is much more frequent, of course. It doesn't matter, okay? It will always increase by the same amount. So that means that basically I can tessellate my black hole. I can count how many bits of information it has per photon, okay? So if I have now a black hole radius R, I can sort of see its area A, and I can divide it into segments. And the segment has an area which is set by the so-called Planck length. The Planck length is this thing, the very, very equation at the bottom that you see here. It's set by universal constants and has dimension of length. Okay, it's a really, really tiny number. Length, as you can see, 10 to the minus 35 meters. If string theory exists, people think this would be the scale of what string theory is actually, the strings would be in that scale. We don't know, at least I don't know about that too much. But this is sort of where we actually have problems with gravity and quantum mechanics set problems that things become more perturbative, and we have something fundamental actually happening in that scale, not before that. And you see that this scale emerges naturally when we do this hand-waving argument for finding out entropy of a black hole. Think about this information. Okay, this, by the way, gives you a bound of how much information you can actually store. You can't store more information on the chip. There's some limit to how much you can actually store. Of course, you're very, very far off from that limit, but nonetheless, there's a limit. And you can sort of see here as well the fact that we have information on the surface of the black hole. That is similar to what you have in holograms. Remember holograms, like you have the credit cards and elsewhere. It looks like a 3D image, okay? Taking the 3 beams with the beam splitter that you actually had, and the optic that you have interference and so on, the phase differences. But actually, it's a two-dimensional. It's in 2 dimensions. And if you actually break it into pieces, you can see 3-dimensional structure, but it'll be less accurate, okay? So basically, a black hole is in some sense a hologram, in the sense that it has information which is stored on its surface area. By which I mean the information content is proportional to surface area. Okay. If you are wondering how far off we are from actually achieving this limit, we're very, very far off. This is currently the state of the art. This is what I found so far. So you can store, 1 bit information in 12 atoms, and atom is a scale of 1 angstrom, and angstrom is a scale of 10 to the minus 10 meters. Whereas a Planck length that you see here in front of you is 10 to the minus 35 meters. So we have quite a bit of way to go, of course. But nonetheless, it's quite interesting that we have some. There are other limits as well, which are actually more practical, which I won't get into, which are actually much stronger. Now, let's think about what this implies for things around us. Suppose you have a rubber band, and you take a rubber band and you stretch it. And you stretch it very, very quickly, and you put it across to your lip or to your forehead or something, and you ask what happens. You don't do it so hard that it snaps and it hurts. You just do it quickly, it doesn't snap, and just, it turns out that you'll feel it's actually hot. Okay? And that tells us a lot about what the relations in information and entropy. Okay, it wasn't as scary, of course, in this way, but in terms of what's a logical conclusions, this is sort of the origin of that. Why is that the things heat up? That the band that we actually, this rubber band heats up, and I search after very, very quickly. The rubber band is basically composed of these very, very long molecules. And these long molecules initially was a sort of a liquid, and then you put some sulfur ions and you bake it and you cool it down. It's like localization, and then it becomes rubber. Okay. And in the beginning, before you actually, if you search all the way through, so you have this tiny mesh of these long polymers, which are tied to each other by these sulfur ions. If the rubber band is stretched all the way through, then you'll see what's shown here, I apologize, on the right-hand side, which is shown in the, I hope you can see it, because I cannot see it completely because of my Zoom screen here. But basically, it's pretty clear that all the it's stressed straight lines. There's nothing, no information I need about this. If it's stretched all the way through, I know exactly what it looks like microscopically, just straight lines. It's all parallel to the direction that we just stretched. I got the symmetry, stretch it this way, all the mark is oriented this way completely, and there's no uncertainty that I have about it. On the other hand, in the beginning, before I pick it up and stretch it, all these little jumbled mess, and lots and lots of possibilities. So the information that I had in the beginning vis-a-vis the end changed, okay? Entropy changed, okay? So this is more structured than this thing, okay? There's more information I need to actually have here to tell you what in detail what actually happens, okay? During my original recording, somehow the connection became bad at about this point. So this is recorded a bit later, but it's a continuation of the same talk. And I'm going to make it slightly longer because I'm going to also include answers to questions that were asked, and which the audience can actually hear what I was saying quite a few times. Okay, so coming back to what we just discussed, the last thing that you actually saw, rubber bands behave the way that they do because of entropy. So in this state here that appears on the left, the system has, as we just discussed, a lot of entropy. You need a lot of information to describe exactly where all the polymers are, the orientation, the location. On the other hand, on the right-hand side, as you just heard, not such much information is needed. There's a special direction, which is the axis along which the rubber band is stretched, and the amount of information needed to describe the system is not nearly as large. So in snapping back from configuration B, the fully stretched one, to configuration A, the system restores its entropy. And that's really the origin of elasticity of rubber bands. It's basically driven by entropy. And that driving force, the entropic driving force, is larger and larger at higher temperatures. So generally, quite universally, as temperature increases, entropic effects become more important. And this is also true for the rubber band that we just discussed. So in other words, rubber bands become more and more elastic as you go to higher temperatures. Of course, if you go to too high temperatures, they will melt. But if in a regime that actually rubber bands, they'll become more and more elastic as you go to higher temperatures. And conversely, if you go to low temperatures, they'll become more and more brittle. They will not be nearly as elastic as it would be at higher temperatures. And this, unfortunately, appears in many situations, and unfortunately also, fortunately and unfortunately appears in many situations, but very, very unfortunately, it also appeared in the disaster of a space shuttle, which some of you might remember, in 1986. So the reason for the explosion that occurred very shortly after it took off, the Challenger took off, is because the O-rings that were vital, very, very small components of the shuttle, but vital to its operation, they were very, very brittle. So this was a cold morning, and the O-rings were very, very brittle, and they just snapped very, very shortly after takeoff. And this was demonstrated by Richard Feynman. So here you see a picture of him in this commission, and what he did to illustrate this effect is basically take the O-ring and put it in a glass of cold ice water, and take it out, and apply pressure to it, and just see that it breaks quite readily. And this is unfortunately exactly what happened. Now, this effect that we just discussed between heat and entropy, so the one we alluded to earlier in terms of rubber bands that give off heat when you stretch them because entropy goes down, so heat is generated, is also not only in rubber bands and rubber in general, but also in many, many systems all around us. So for instance, if you think about ice, for instance, and you take ice, which has a regular structure, like for instance, the structure right here, okay, and you heat it up, it becomes water, which is a structure that you see in the cartoon-like fashion here. Okay, so to describe ice, we don't need as much information to describe water. And more generally, if you have any periodic solid, you don't need much information to describe it as you nearly as much as you need to describe a fluid. And as you actually go from a fluid to a solid, the system expels heat, it cools down. So information is lost. You don't need as much information to describe water as you do ice. Information is lost. And hand in hand, heat is expelled, just like in the case of rubber band. So all this points out to a deep relation between entropy and heat. By the way, just in case you're wondering, in this particular cartoon of ice, the red spheres correspond to the oxygen atoms, and the blue spheres correspond here, and the white spheres here correspond to hydrogen atoms. And so you see the pattern that you have here of H2O, the two hydrogen atoms are close to each one of these oxygens, with the usual water molecules, but now they're arranged in this nice periodic pattern. Okay, and around each hydrogen, you will see, each oxygen, you will see that you have two hydrogens which are close to it, the original H2O molecule, the two hydrogens are close to it, and they're two further away, like this one here and this one there, that you don't see on this axis, and so on. And this is how typically ice actually is formed, and there are various phases of ice. But the point about this cartoon is not so much speciality of ice, how it's structured, but rather the fact that there's structure there, and it's periodic, and you don't need as much information to describe it, because once we describe what happens in the so-called unit cell that you have, which repeats itself ad infinitum over the entire lattice, that describes the entire structure. Of course, at finite temperatures, you have also thermal fluctuations, you have imperfections, and things of that nature, but those are perturbations about the ideal structure, which really does not require much information to describe it. Okay, so coming back to the moral that we have, there's a relation between situation where we have heat being expelled going from the fluid to the solid, and also information being lost. But here we need a lot of information to describe a system vis-a-vis this system, just like in the case of rubber band. So all this, as I mentioned earlier, points to a deep relation between heat and entropy, because after all, entropy is a measure of information, as we just discussed in great detail. And indeed, such a relation exists, and it's a very, very simple relation. It's encapsulated in the equation you see in front of you. Okay, I'll describe the equation. For those who do not take equations that much, don't worry about it. I'll describe it in words quite a few times. So what you see on the left-hand side of this equation is basically the change in entropy. So as you go from, let's say, fluid to a solid, information is lost, entropy goes down. So that's a change that you have between the final state and the initial state. On the right-hand side, you have the amount of heat that goes into the system. Okay, so Q is a common notation people used for many decades by now, if not centuries, for heat that goes into the system. And that's exactly what naturally appears, given the examples I just showed you of rubber bands and ice and water and things of that nature. Now, there's actually a very big difference in the list between the right-hand side and the left-hand side. Not only we're dealing with heat on the one hand and entropy on the other hand, but notice if you look at this equation, we divide by temperature, we divide by T. And that makes a crucial difference, because what we have on the right-hand side, namely heat, is we can measure it, we can feel it with our hands. So the morning, the talk that I gave was a pretty cold morning. So you can rub your hands together, and as you rub your hands together, as you know very well, you generate heat. You can, of course, take stones and you can grind them against each other and generate fire like our forefathers did. So friction generates heat, as we all know very well for millennia by now, not millions of years by now. Million years by now, but there's the heat that we generate depends on the history. So for instance, if I actually rub my hands for a very, very long amount of time, I'll generate more heat. The longer I do that, the more heat I generate. Okay. On the other hand, the information change depends only on the state. If I have a particular state that I'm showing you, it contains a particular amount of information. It doesn't care how I form that state. It's a unique assignment that I have for a particular state. How much information, how many bits do I need to describe that state? So the left-hand side doesn't care about history. It cares only about maybe the initial and final states per se, but not on how we evolved from the initial to final states. That's completely irrelevant, because if I tell the initial state over final state, I can ascribe to it uniquely the corresponding entropy. The entropy of the final state and entropy of the initial state are different, but those are determined uniquely by the states themselves.
And on the right-hand side, we actually have to describe how we actually go from initial state to final state. If I rub my hands longer, I'll generate more heat. If I don't do it this long, I generate as much heat. If I do it vigorously, I generate more heat, and so on. But at the end of the day, if I just stop rubbing my hands and I look at the initial and final states, okay, what really matters for entropy is just the states themselves, not how many times I rub my hands against each other. So this difference, we can visualize it in this sort of cartoon. So in this cartoon, what's plotted here, so this is just a general three-dimensional cartoon. I just took it from this website, which would have to do something completely different. But the point is that here we have a function, namely the entropy, that assigns uniquely a value to any point that you have in the plane. So if I give you a particular configuration, let's say my hands, I look microscopically, or water, if I zoom on it and see exactly what's going on there, or rubber bands, if you can zoom on it and see exactly what's going on there, or any other thing we want to think about, if I could really look at the exact conditions and see how they behave and how they're ordered, and I ask what information is actually encoded there, I would get a unique number of bits. So I have a unique assignment to any given state of the system. So I have it for the final state, I have it for initial states, and any point that you have in that plane, in this plane that you see in front of you, has a unique value of entropy. So this vertical axis here is a measure of the entropy. Now imagine you evolving, as you rub your hands together, for instance, from this initial state to this final state. You can do it in a multitude of ways, of course. You can go straight up like this. Maybe you could take a trail which goes, meanders around and goes like that. At the end of the day, there's a unique difference between the altitude that you would have here at the final state, this final values, final altitude, this final entropy, and the value that you have of initial point, with final altitude in this graph, the entropy, as we think about it in this cartoon, what I want you to think about, it's a unique value. So the path between these 2 points is completely irrelevant. However, the entropy, so the entropy itself, the entropy difference, which I want to emphasize, doesn't really care about what path you choose, okay? But on the other hand, the amount of heat that you actually generate as you go from one to the other, that does care about what path you choose. And so on the right-hand side here, delta Q over T, you do care about the history, okay? And the left-hand side, you don't. So by dividing miraculously the heat change for a reversible process, by the temperature, you get something that doesn't care about how you evolve from one state to the other. And this was found 200 years ago by Carnot. He was a French engineer that was working in Egypt. He was thinking about abstract engines. He was trying to idealize them and thought about limits that you would have for engines. It was a practical question. But he came across, as he was thinking about it, he actually noticed that if he ran an ideal engine in the cycle, and it came back to the same initial state, even though there'll be heat generated, there'll be some work that's performed, etc., the total amount of entropy change, if you define entropy in this way, will be zero. Namely, it cared only about the initial and final states, and if initial and final states were the same, the entropy change will be zero. Now, the entropy change has a few fundamental properties, and one very notable fundamental property, a crucial one, is the second law of thermodynamics. And this states that you have any closed system, the entropy of that closed system will never decrease. It can, at best, stay the same, and in general, it will increase, okay? And this defines an arrow of time. So even though the equations of motion, if you typically think about them, are microscopic. If I have a movie and I'm running backwards, it might look artificial if I break an egg and I see all the pieces go back together. And on the other hand, but fundamentally, the equations of motion I would have, and Newton's equation of motion, if I say think about classical mechanics or other equations of motion, if you think about quantum mechanically, they're all reversible under arrow change of time. But we know from experience that time only goes one way. And this is really captured in the second law of thermodynamics. So the entropy always increases or stays the same. Okay. Now, this equation here, as I mentioned by now quite a few times, captures a vital relation between entropy, which is information, and heat, which relates to a form of energy. Okay, I should say that this, in physics, the entropy that we think about typically is not exactly information entropy. It's the same thing up to an overall prefactor, which is a constant number throughout. So if you multiply the entropy by a constant number, which is called the Boltzmann constant, times the natural logarithm of 2, that gives you this entropy that appears in the thermodynamics. As it's mechanics, this S that appears here. So it's basically just the usual Shannon entropy up to an overall innocuous prefactor. Okay, so this relation shows us that there's a fundamental connection between the two things, between information on the one hand, the left side, and heat or energy or work on the right-hand side. So I say work because there's another fundamental relation, which is called the first law of thermodynamics, which states that, as I just mentioned a few seconds ago, that heat is a form of energy, essentially. And if you look at what changes to a system that you actually have in the macroscopic scale, you can associate with them work that's being done. In the microscopic scale, we cannot really visualize, you can't really see what's going on there. Those processes can give rise to heat. So there's a relation between heat and work we had associated with delta Q, and that's the heat that we have, and the entropy for work, the information content. And this relation between the two things, even before people were thinking about entropy in terms of information, which was only in 1948, I say only because entropy was introduced by now 200 years ago in physics, bothered many, many people. In particular, what bothered many people was the arrow of time, and in particular, second law of thermodynamics. And one of the people that bothered was Maxwell himself. So Maxwell, from Maxwell's equations, he spent a lot of time thinking about the second law of thermodynamics. And he tried to really think about it in a deep way and try to think about a paradox that maybe we had to resolve to understand what are the underpinnings of the second law of thermodynamics. So he thought about there's basically a sentient being that could sort of visualize all the molecules that move around. And this being could close and open some shutters, and in such a way to segregate the gas that appears into sort of a region that has hot molecules that move quickly with high speed, and those that move slowly, those that are cold, and in this way generate basically a heat difference, and the heat difference could do some work, and you could actually generate work almost for nothing in this way. Or basically you could take what you would have from some heat source and convert it purely to work. And that's not possible. That's one of the older formulations of the second law of thermodynamics. And this problem was thought about by many, many people since, including Leo Szilard, who was one of the fathers of atomic bomb. And this connection between information and entropy is information, and heat and work was later was further yet pushed forward by Landauer, who really obtained fundamental limits in the amount of heat that's being generated when you have computations. So let me first describe to you the Szilard engine. So imagine that you have a molecule that's bounded, it's confined to this box. The whole box is surrounded by heat baths, so the whole thing is a temperature T. Temperature does not change. So this molecule can bounce around, but as it bounces around, temperature doesn't change. It's hard to talk about the temperature of a molecule because we typically ascribe temperatures to large systems. But then let's think about just one molecule that we have here. Okay, so we just described this average kinetic energy as set by the temperature. Now imagine that this demon lowers down this panel slowly, and then at some stages, the molecule is confined here to the left hand. Of course, a priori, the molecule could have been either on the left-hand side or right-hand side. It require, assuming that this is sort of midway between the left and right ends of it we have in this box. Once this wall goes down, slides all the way down, we would need one particular information, this is to say whether the molecule is on the left or on the right, to describe the state of the system in that regard. But let's imagine in this cartoon that the molecule happens to be on the left-hand side once this is done. So once this is done, and the sentient being sees it actually the molecule on the left-hand side, he or she can attach a pulley and maybe a small mass to this pulley. And as this mass hits this piston, this wall that can now slide, you can actually pull up this mass, And in pulling up this mass by virtue of these fluctuations that we have, this motion that we have of this molecule, for heat bath, you can actually pull up this mass. So basically you can convert thermal energy that you have from the heat bath that moves around this molecule into work, useful work by pulling up this mass. Okay, so and this mass this wall slides all the way down, this molecule keeps bumping with it over and over again many, many times, and you do some useful amount of work. Then you can do it again and again and again, many, many times. So this converts basically heat that you have into work. Okay, what you have from the surrounding ambient environment, the heat reservoir, as it's called, to work. Now, there's of course a catch to this. It doesn't work so well as it's described here. And the point really is, as was emphasized by Landauer, that to run this system, to run this daemon, you actually need also to think about work and heat. So our brains, computers, and so on, things that process information, that require information, are like any other machine that you can think about. They also generate heat, and they do some work, and they generate heat. And the fundamental limits associated with that. So as you can sort of see in this cartoon, by knowing information, you can actually do some useful work, but erasing information generates entropy. Let me explain to you what I mean by that. So imagine that this mass was pulled all the way up, and now again, this daemon slides again this wall down the middle and sees where it is and so on. So if the daemon does not know where a molecule is, then to specify where a molecule is, you need one bit of information. And the daemon can only store so much amount of information. Every time he or she sort of forgets where it is, doesn't know again from where it is, and again, you have to know where it is. You have to supply information if it's on the left-hand side or right-hand side. But that amount of information, as we just saw, associated with heat, examples that we had for rubber band and solids going to fluids and so on. So as we extract work and as we sort of do this process, we have to every time start afresh. We have to again see where it is, and this process is erasure information to start afresh and figure out where is actually my molecules at the left side, the right hand side. That process generates heat. Okay, so just to emphasize this point. So running the daemon itself, running any machine, including ourselves, our brains, generates heat. Okay, and there's a limit to how much minimal amount of heat it needs to generate, including in computers. And you might ask how do modern computers fare relative to this limit? Again, we're very, very far off. Not nearly as far off as we were in talking about fundamental limits that we have to measure compression, by talking about black holes. But in this case, we're about 6 orders of magnitude, basically a factor of 1,000,000 away. We'll land our limit. So this brings into the next topic, which is machine learning. So again, I explained to you that processing information in brains and computers is phenomenically just what you would have from usual other machines. And now it's all too natural to think about machine learning, which is very, very hot these days, and for a good reason. It has many, many applications. And I'm going to talk about it also because in this field, we use a lot in entropies. We actually, when we so-called train our system to figure out what we wanted to figure out, we use typically entropic measures. So let me explain to you what I mean by that. So one canonical example in which machine learning is really it's good at many things. We don't know why it's so good. But one example it's really superb at is identifying images, for instance. So you have images of dogs and cats and so on, and you give these images to the computer and you ask it, is it a dog, is it a cat? Whatever probability is it's a dog or a cat. So in a nutshell, and sort of symbolically, what we have is we have this image. We pixelate this image, okay? We run it through this artificial neural network, and out come outputs, which are these numbers that you see here in front of you, okay? And from these numbers, and by the way, the actual architecture of this thing is actually very, very simple. We don't know why it works, but the architecture itself is very, very simple. It tries to emulate what happens in our brains. Basically, these are so-called artificial neurons. There are different layers are linked to each other. So all the neurons here are linked to the next layer, and all the neurons in this layer are linked to the next layer, etc. And they basically, each neuron is linked to all the neurons in general, a priori. It's possible, that doesn't have to, but it could. And there's very weights associated with how much it's linked to the other neurons. Okay, like when you think about sort of synapses and axons. And here is just the output that we would have for these neurons. So this comes in, okay, it's all processes together, typically by some combination of just multiply the inputs that you, the outputs that you have here by some numbers, you sum them up, and you have what comes in here. Here is some nonlinear function acts on these sums. And then again, it goes to the next layer and the next layer, etc. And if we have more and more layers, this neural network is called a deep neural network. The more layers it has, the deeper it is. And in reality, when we have images, typically we use what's called convolutional neural networks. Again, these are technical terms I want to get into, but the important thing for us are thinking about entropies. And this is really a key ingredient in modern machine learning. So what is it about here? So when we have the inputs as pixels, we do some black magic. We find out the ideal weights that we have to put here and the so-called biases. And then we have some numbers here. The numbers we assign probabilities to by using some function that converts continuous real numbers to probabilities with sum is equal to a value of 1. And for those of you in the audience who are physicists or like equations, mathematicians, scientists, so this quantity right here is called in computer science typically the softmax function. And those of you who are physicists and engineers and chemists might recognize this is none other than Boltzmann distribution. It's exactly the same thing as we have for energies in physics when we have some temperature and we have energies. Energy that's basically sometimes these numbers or by these outputs y. At any rate, we have outputs. We convert them to probabilities that sum to a value of 1. And so if you're given the image, after you pass through this black magic stuff here, and you have the outputs and you make them into probabilities, you can read off a probability that the image is a dog, in this particular case, 77%, 5%, it's a cat, 11.6%, etc. And you can contrast it with what it really is. So of course, we know it is a dog, so we can tell the system, the computer, in reality, what you have here is a dog. So we can penalize it, but not saying that the probability of a dog is 100% by ascribing it to only 77.5%. And of course, if a prediction of the computer was even worse, if it would say it's a horse, we would make it even a higher penalty. So we have to design a penalty, and the penalty is a quantity that we minimize, a so-called loss function. We minimize it, we basically go back in this network, so artificial neural network, and readjust these weights, so-called back propagation, until so it says the error is minimized, and now we have a new image. Again, we do the same thing, we go forward, see what the loss function is, go backwards and adjust the weights and biases so it gets the right result. Do it again and again, many, many times, with many, many images. And at the end, we have a neural network, which is really fantastic, quite often, in predicting what it actually sees. So what is this magical loss function? The magical loss function in tasks associated with classifications, with, for example, if it's a dog or a cat or a horse or a cheetah. So there are 4 classes that we have here. It can be any one of these 4 classes, and there are 4 probabilities associated with all these 4 classes, which of course sum up to 1. So the probability of being a dog, probability of being a cat, horse, cheetah. Okay. And these are real probabilities that we know what the real probability is. In this particular case, the real probability is 1. It's a dog, and anything else is 0. The computer thinks in a particular cartoon that it's a dog only 77.5%. So how do we penalize it? So basically we contrast the probability that the computer thinks it is. So I apologize. I should, in my own slides, I use this as Q. This is an image taken from somewhere else. So that computer thinks that these are probabilities that it's a dog, cat, horse, and cheetah. And there are the real probabilities, which are these probabilities. So it's probability 1 that being a dog, probability 0, anything else. And we look at this quantity, which is very, very similar to the Shine entropy. If we had the QI, what the probability that the computer predicts this quantity to be, equal to PI, what it really is, this would be the Shine entropy. And indeed, if you try to minimize this quantity, if you're given the probabilities PI, and you ask, whatever is the distribution that you would have QI, whatever probabilities the computer should guess QI, that would give the minimal value of loss function. So it really doesn't have to readjust any of the weights and biases. Whatever happened in this black magic part of the deep neural network, and also deep neural network, or it could also be other architectures. Doesn't have to always be neural networks as well. So in that case, the QIs were equal to PIs. And the way to do that is, we can do it with calculus, but just to give you even a more direct way of thinking about it, is with just intuition based on what we just discussed earlier. We saw earlier that the information content of any event that we have, any problem, any alphabet, any letter that we have, any configuration that we have, is equal to the log base 2 of one of the probability that we have that state, okay, which is the log base 2 of that probability of a minus sign, of course, because the log of one over something is minus the log of that something. And what this quantity actually measures is how many bits of information do you need to have on average if the data that you have comes at the probability pi, and you think it actually comes at some probability qi, so you construct your code words to squeeze information, as Shannon did, used based on some sort of architecture that you have, that you assign some number of bits, something particular way to do it. So you minimize the total amount of bits required, and you have minimal information content. The number of bits that you actually use to do that is just equal to information content. You squeeze it all the way through. Okay. So if the data that comes streaming at you is not what you think it is, then what the number of bits that you use is going to be larger than the channel limit. Channel limit is the absolute minimum. So in general, this cross entropy is indeed always going to be greater than or equal to channel entropy. And in reality, it's always going to be bigger than that, unless the probabilities really exactly match. So basically, encoding schemes that you have for bits is exactly right. One you should use for what really data that really appears. It's not matched to something else, not optimized to something else, which is not what you should think about. Okay, so this is a quantity that computers typically minimize, and by minimizing this loss function, they adjust weights and biases, and they do it over and over many, many times, and you get fantastic results in many situations. They surpass humans in many, many situations. Okay, so this is what we do. I hope it all was clear. So lastly, I'll tell you a little bit my own work, and of course, I'm one of many working in these fields. So in my own work, we actually try to use machine learning and entropic measures, information theory measures, to describe physical systems. One of these systems that we looked at some time ago by now, and then we joined work with Ken Kelton in our department, was to find out the structure of glasses. So glasses are amorphous, right? They're not crystalline solids. They have seemingly amorphous structure. Not seemingly, they have amorphous structure. And you can sort of see local structures that you have. If you do scattering measurements, you can see peaks and valleys, things like that. But there's nothing as clearly, it's not that something is periodic as it is in the crystal. You don't have a very, very sharp peaks as nearly as much as you have in the crystal. You have X-ray measurements, for instance. So can we actually find structure here? And is it meaningful? And so one way to think about it is to imagine that you take the atomic structure, which is actually shown here, is from data from Kelton's group, experimental data, the scattering measurements were done, and run on this so-called reverse Monte Carlo to find out the most likely atomic configurations, and then do what I was talking about today, using basically machine learning and entropic measures to find out the basic clusters that we have in this multi-atom system, lots and lots of atoms that you have. Okay, so here are 10,000 atoms, and basically what's done is we imagine that we take this bunch of atoms and we smash it on the floor and we break into pieces. And if we do it many, many times, and we always break into the same pieces, then these pieces are somehow cohesive, and they're so tightly bound, they have correlations within them, and fewer correlations or less connections between the pieces that are always disjoint. Okay, so in this particular case, the alloy at hand was yttrium, aluminum, iron. So you see the three spheres there with the Y, Al, Fe, ferrum. So this is just, of course, these are the different atoms that we have, and the corresponding radii of atoms associated with these three atoms, that you see in the cartoon in front of you. And the colors correspond to the different clusters that we actually find. So we used a so-called unsupervised machine learning algorithm. This actually was before people typically call it machine learning. I mean, machine learning, of course, is an old field, but it came to the fore anew in the last 10 years or so, because of really amazing advances that were done. So this was actually at the time we called it clustering, or basically thinking about so-called community detection. You find what communities or clusters that you have in the system. And we find these very large structures. So you see you have all these purple atoms, they form these large clusters of the green atoms forming large clusters. It's not that you have just numerous bigger atoms. It actually involves many, many atoms, even though there's no obvious structure there. But nonetheless, if you actually do this operation many, many times and look at the correlation that you have, what you find is that you have a very, very high value of entropic measures, information for your measures. So what's supplied, for instance, in panel A is a so-called normalized mutual information. Is if you do this operation many, many times, measure over many, many times on the floor, and look at correlations, you will find that they all agree on what the final result is. So a value of NMI for mutual information of 1 is maximal. So normalized means the maximal value is 1. And indeed, you see here that you have a plateau. So let me make this not as big, so you can actually point to it. You have a plateau here, which is really doesn't have a very, very high slope. So it's really almost flat. This is really a plateau, in which the normalized mutual information is a value of almost 1. So this is actually a very, very stable configuration, partitioning that you actually have on this scale. And this corresponds to structures that look like this, okay? And you can do other measures, of other entropic measures like the entropy itself, the so-called variation of information. They're all interrelated to one another. And again, you see that you have something happening around that scale. That is most pronounced when you think about the measure at NMI, but you see it also in the other measures. Number of clusters, sort of some dip there and so on, and sort of stable over that region, which is essentially this region here. So there's something going on there. And because NMI is so high and other measures are also quite stable, you can actually dig deeper to understand what really is going on there. In simple cases, like for instance, some of the metallic glasses that have a small number of atoms, or silicates, you do have, these are certain glass formal types. Silicates are what you have in window glasses quite often. You can really ascribe these structures to rules that you have of local arrangements, and you can actually see how these local arrangements generate the structure goes from one side of the system over onto the other, or more generally, in very, very large clusters. Other situations when you have multi-atom cases, it's pretty hard to visualize because you have many, many components, unless you have stability that appears here. Okay. So this is what we did, but of course, there are many other people thinking about this sort of similar questions. And shortly, I mean, a few years after we did this, there was also beautiful work that was done by Andrea Liu's group, and other works that were done since. So she was using another approach. She was using supervised machine learning for more conventional machine learning, and when I showed you for loss functions, and also people use specific point analysis, which we did not discuss. There's a whole big field, lots and lots of techniques here. But the idea is to find structures that you have. And typically nowadays, quite often people use machine learning to do that. And they use entropic measures quite often, not always, to drive the computer to actually find these structures. Lastly, I'll tell you yet another example is that of phase transitions that you have in machine learning, again, which are found quite often by thinking about information for your measures. And of course, in general, if you have a phase transition, its entropy, as we discussed, for instance, the solid to liquid transition, is a change of entropy that appears, which is quite profound. And latent heat, some of you might know you need some amount of heat that you have to convert ice into water. The thing is not changed, but you have to pump heat into the system to actually melt all the ice into water, and then it keeps going. There's a profound change that you have in the entropy and other quantities. And this also appears in transitions in machine learning. And you can particularly use what we tried to use at the time, normalized mutual information, to ascertain phase transitions. So not to think about only Shannon entropy, but also more general correlations that you have between different sets of data, different probabilities, which is NMI I was referring to earlier. Again, if these clustering problems I mentioned earlier, just in the last slide, applied not only to systems of atoms, but also applied to general data sets that you have. Also artificial data sets, not only the ones I showed you, but artificial data sets with random connections. You have some structure there, but you obscure it with random connections. And you ask, until when can the machine actually find the structure there? And then you find as a function of noise, which is this quantity here, this P out, as a function of temperature that you have in the heat buff algorithm, you find that you have a very, very sharp transition between a phase and you can actually find the structure there, which is this phase right here, with this small value of this noise, okay, at typically low temperatures, but not always, because actually temperature, because it can actually have a good effect, because it can allow you to anneal to the right solution. And you see the same sort of phases also here. And this quantity susceptibility, as we called it, is how much accuracy improves if we run the system more and more times. So if you can't find any structure there, right, more times you won't find anything new there, it's still just as bad as it was before. If the structure is already obvious, you have to run it more times in order to see it. But if it's just really barely there, it's really hard to see. If you run it more times, it will become more visible, and this is when it actually peaks. And using other metrics in information theory, not only information, but also Shannon entropy itself, variational information, others, including just energy itself, and correlations as a function of time, and also looking at what you evolve the system backwards and forwards, with so-called waiting times, it's correlation functions, and trying to collapse them universally to some data. You indeed see that you have phase transitions in these machine learning type algorithms and problems. And you can see them with these entropic measures. Again, we're one of many working and thinking about this. So again, so shortly after we had our work, only a few months afterwards, there's a beautiful work by DeSalle and co-workers, which was a different approach. We were looking at things numerically for very large networks, just doing brute force. We had a very, very nice analytic approach. So basically, these works complement each other, and many other approaches, works that appeared since. So there are certainly phase transitions in machine learning, and these will appear only for large systems, okay? And these are also known to appear over problems that are complex, random problems that are complex. Okay, so here I'll basically stop. I'll just flash for you conclusion. Basically the question I was trying to address for you from different aspects is what is information? And the answer is that we're still learning and we're collecting new information and insight. And there are many things, of course, I did not discuss, all too many, like, for instance, quantum information, which is a very, very hot field these days, which has many problems, many of them are really very deep. And unfortunately, this is recorded after the talk itself, but I try to emphasize aspects that were asked during the talk and the audience couldn't hear me.